Hello mathematicians, thank you for joining me today as we start to look at rings. Just as a note, since we are nearing the end of the semester, I'm going to kind of throw a lot at you today, and I'm going to try to relate it to the things we've done with groups, but I'm not going to give a full viewing of rings. So if you want to learn more about these, I would highly suggest going through the book on these chapters and spending some time working with it so that you get more comfortable with these things. The first thing we need to do is realize what a ring is, and so I'm going to give the definition. A ring R is a set together with two binary operations, whereas a group was just one binary operation that we normally denote it with the multiplication. Here what we're going to have is an addition and a multiplication. In order to call it a ring, what we're going to have is that R together with the addition is going to be a commutative group. That is, it's going to be closed under addition. It's going to be associative, it's going to have an identity, and everything's going to have an inverse, but also it's going to be commutative. So we start off with a commutative group for addition. Then we add in this other operation, the multiplication, and what we need in order to be a ring is that that's going to be a semigroup. So if you remember back to when we talked about semigroups, it just means that, well, it's going to be closed under the multiplication, and the multiplication is going to be associative. Furthermore, in order to be a ring, we also have to satisfy left and right distributivity. That is, that we satisfy these equations below, that A times B plus C is AB plus AC, and B plus C times A is BA plus CA. So for some normal examples that we've seen is, notice that the integers is a ring. Well, we know that the integers is a group under addition because it's closed under addition. The addition is associative. It is also commutative, which we'll need. The identity is just 0. And if we have an integer, then say a, then negative a is also an integer, and negative a plus a is 0, so we're closed under additive inverses. Therefore, z is in commutative group. Now, if we go under multiplication, notice that, well, the multiplication of integers, two integers multiplied together is again an integer, and it is also associative, so we have that indeed Z is a ring. If we follow the same procedure, we get that the set of rational numbers is a ring, and so is the set of real numbers. Now, if the ring has a multiplicative identity, instead of saying the multiplicative identity, we can also call that a unity. So the multiplicative identity is a unity, and if a ring has a unity, it's called a ring with unity. Note that it won't necessarily have to have a unity because we didn't define a ring as having one. And so if we think back to our group talk when we talked about semigroups, would be, well, a ring starts off where the multiplication is a semigroup. If it has a unity, then under multiplication we'd have a monoid, and we could talk about those things as well. Now, we could also say, what is a commutative ring? Well, notice every ring is going to be commutative for addition because we defined it as such. So when we say commutative ring, we really mean that it's commutative under the multiplication. If we look at our previous examples of the integers and the rationals and the real numbers, each of those was a commutative ring because the multiplication is commutative. Also, each of those had a unity, which is just the number 1, because 1 multiplied by anything is just the anything. So there we would have, those are all commutative rings with unity. Just to give you an example of where we don't have to have a unity is we could look at the set of 2z, that is the multiples of 2, or all the even integers. So if we use the usual addition, notice that, well, if we take an even plus an even, we get an even. And the addition is still associative because the addition for the integers is associative. The identity would be 0 is also even, and 0 plus anything is the anything, so we have additive identity. And if we take an even integer, say a, then negative a will also be even. So therefore, we have something where everything that's even there is closed under addition, it's associative, we have an identity, and we're closed under inverses. Therefore, 2z is a group under addition. Now, if we look at it under multiplication, what we have is an even multiplied by an even is indeed an even number. However, there is no unity here because if we try to find a unity, it would be 1, for example, but 1 is not even, so it's not in the set. So we take any even number and multiply by any other even number, we're going to end up changing the number because we're going to end up multiplying by 2. Therefore, there will be no multiplicative unity. However, this would indeed be a commutative ring because the multiplication would still be commutative. Now, if you wanted a non-commutative ring, what we could look at is, say, the set of matrices are the set of 2 by 2 matrices with real entries. And so we've actually looked at this one before, and we said, okay, if I take the set of 2 by 2 matrices under addition, it does inform a commutative group. So therefore, we have that, okay, under addition, we have a commutative group. Under multiplication, we know that matrix multiplication is closed. However, we have seen examples of where this was non-commutative, so somewhere where AB was not equal to BA. So in this case, we would have a non-commutative ring. There indeed will be an identity, which will be the matrix consisting of 1s along the diagonal and 0s everywhere else. So this would be a non-commutative ring with unity. But the idea here is that, yes, we can have rings with or without unity. We can have commutative rings or non-commutative rings. Both of those are possibilities. Now, if you'd like to see some of the details of this, we did go through that before, but I'll link in the description where the formal write-up of showing that this is a non-commutative ring is. Alright, the next thing we're going to look at is if we have a ring R, we're going to say that if there exists an A and B in R non-zero, so A and B are non-zero elements of R, if we can get that A times B is equal to 0, then we're going to say that A and B are 0 divisors, because if I multiply them together, I get out 0. Notice that this does not happen in the real numbers or the integers or the rationals. If I ever take any of those and multiply them together and I get out 0, then one of the terms had to be 0. However, in general, we can indeed get 0 divisors. As an example of that, let's just look at Z4. Notice that if we look at the multiplication, well, if we try to find 0 divisors, we can take 1 times 2 is 2, so that doesn't work. 1 times 3 is 3. 2 times 2 is 0. So there we go. We have a 0 divisor because 2 times 2 is 0. 2 is not equal to 0, and 2 is not equal to 0, so that is a 0 divisor. 3 would not be a 0 divisor because 3 times 1 is 3, 3 times 2 is 2, and 3 times 3 is 1. So the only 0 divisor for Z4 would indeed be 2, but we would have a case where I multiplied two non-zero numbers and got out 0. Now, if I have a commutative ring with unity that has no 0 divisors, we're going to call that an integral domain. Now also I'm saying here that the unity E is not equal to 0. So if we had just the ring consisting of 0 itself, then we wouldn't call that an integral domain. But if we have a commutative ring with a non-zero unity and no 0 divisors, we call that an integral domain. So if I want to see that Z3 is an integral domain, what I'll have to do is show that it is a commutative ring with unity and it has no 0 divisors. So the best way to do that is really just to make up a Cayley table and see what the products become. Alright, so we're going to try to show that Z3 is an integral domain. So what I'm going to do is just go through and find Z3 by finding the Cayley tables for both the addition and multiplication. And so what I'm going to have is under addition I get 0, 1, 2, 0, 1, 2, and so if I add, I get that 0 plus anything is itself, 1 plus 1 is 2, 1 plus 2 is 0, 2 plus 1 is 0, 2 plus 2 is 1. So under addition we have, well, this is indeed a commutative group because if we add in any direction, 1 plus 1 is the same as 1 plus 1, 1 plus 2 is the same as 2 plus 1. And so as we go through, yes, this is indeed a commutative group, and we have actually shown that before. If I look at the multiplication now, what I get is 0, 1, 2, 0, 1, 2. And so 0 times anything is 0. 1 times 1 is 1. 1 times 2 is 2. 2. And then 2 times 2 mod 3 is just 1. And so what I have is that Z3 under addition will look like this, and it'll be a commutative group. But under multiplication, we'll get this. Notice that this is not a group because, well, we don't have any inverses for 0, say. This would be a semi-group because it is closed under multiplication. And if we go through and check, yes, it is indeed associative. And if I look at this, I can also see that there is a unity because 1 times anything is what I started with. That is 1 times 0 is 0, times 1 is 1, times 2 is 2. And that's true in both directions. So we have that the multiplication is closed, associative, commutative, and we have a unity. The last thing we need to check is that for it to be an integral domain, it's just that it doesn't have any zero divisors. So the point is if I get out 0 as a product, so I'm looking here for zeros, one of the terms have to be 0. So for all of these, this was 0. For all of these, this was 0. So now if I look at the non-zero numbers multiplied together, 1 times 1 is 1, 1 times 2 is 2, 2 times 1 is 2, 2 times 2 is 1. So in none of these cases did we get out 0. Therefore, if I multiply any non-zero elements, I get out a non-zero. So I have no zero divisors. So if I combine that all together, I see that Z3 is indeed an integral domain. So if we go a step further with this, we can say that a ring in which the non-zero elements form a commutative group with respect to multiplication is a field. Notice that if they form a commutative group, well then it's a commutative ring. Since it's a group, it has an identity, so the non-zero elements have an identity for the multiplication. So therefore, this would be a commutative ring with unity. Furthermore, because it's closed under multiplication, if I take any non-zero elements and multiply them, I can't get out 0 because I have to get a non-zero element. So therefore, this will be a commutative ring with unity and no zero divisors. So any field will be an integral domain. The additional step here is that also we'll have to have multiplicative inverses for every element, whereas in an integral domain, you don't necessarily have to do that. All right, so if we look back at the Cayley table we've already made for Z3, we can look through and say that, well, let's make sure that Z3, if I just look at the non-zero numbers, that I end up getting a commutative group. All right, so we already had our Cayley tables from before, so I'm just reusing those. And the idea is that in order to show that Z3 is a field as well as an integral domain, I have to show the extra thing that all of the non-zero elements will have inverses under multiplication. Because, well, we already know that under multiplication, I have that it's commutative, there's a unity, it's associative, it's closed. And so in order to be a group, I really just have to show that all of the non-zero elements have an inverse. Well, notice that the identity is 1, and 1 times 1 is 1, so the inverse of 1 is 1. Also, 2 times 2 is 1, therefore 2 is its own inverse. So if we look at the non-zero elements 1 and 2, each of those is going to be, or have an inverse. And if we multiply any two non-zero numbers, we get a non-zero number. So we end up with, okay, well, the non-zero numbers form a commutative group under multiplication. Therefore, Z3 indeed will be a field. So in the last one we saw that Z3 was both an integral domain and a field, but what I want to look at now is if we find the set of integers, we will actually get an integral domain that is not a field. So to point out here, we know a field must be an integral domain, but we can indeed have an integral domain that is not a field. Now, if you remember back to groups, what we tried to do with groups is start with one or two groups and build either bigger groups or make smaller groups from them. And so we're going to do a lot of the same things we did with groups with rings as well. And so we had the direct product of groups, so now we'll have a direct sum of rings, and we're going to define that as the set being the Cartesian product of R and S. and we're going to define the addition and multiplication component-wise. So if we take an ordered pair AB and an ordered pair CD, then if we add them, we get A plus C and B plus D. If we multiply them, we get A times C, B times D. So we're just taking addition and multiplication component-wise. So let's actually look at Z2 cross Z2 and see what that's going to look like. All right, so if I want to define Z2 cross Z2, the best way to really get an idea of what's going on here is actually just to look at what are the elements and what would the Cayley table look like for both of the operations. So to start with, we know we're going to get ordered pairs where the first entry is either 0 and 1 and the second entry is 0 or 1. So if I write those out, that should be 0, 0, 0, 1, 1, 0, and 1, 1. So those are my elements. Now, I'm going to work on the Cayley table for addition first, and then I'll make the multiplication one. But I'm just going to list these elements 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, and 1, 1. So now if I add these, 0, 0 plus 0, 0 is 0, 0, and then 0, 1, 1, 0, 1, 1, and then 0, 1 plus 0, 0, 0, 1, 0, 0, 1, 1, and 1, 0. And then continuing through, I get 1, 0, 1, 1, 0, 1, 0, or 0, 0 here, and 0, 1 here. And then lastly, we add 1, 1, and I get 1, 1, 1, 0, 0, 1, and 0, 0. So under addition, Z2 cross Z2 is just going to look like this. So I can just say if I add any of the two elements, I end up with another element here. Now this is going to be a commutative group, and we've actually seen that, well, Z2 is a group, so Z2 cross Z2 under addition will form a group. So indeed we will have a commutative group. If we now look at the multiplication, what we're going to do is multiply component-wise. So if I take 0, 0 times anything, I'm just going to get 0, 0. So as I fill these out, that row is going to be 0, 0, but also this column is going to be 0, 0. Now 0, 1 times 0, 1 is 0, 1. 0, 1 times 1, 0, 1 times 0, 0, 1 times 0, 0, so I get 0, 0. And then 0, 1 times 1, 1 is going to be 0, 1. And 1, 0 times 0, 1 is 0, 0. And then 1, 0. And then 1, 0. And then 1, 1 times 0, 1 is 0, 1. 1, 0. 1, 1. So under multiplication, our Cayley table ends up looking like this. Notice that it will indeed be closed because I end up back in this set, and if we check, it will be associative. Now, do I have an identity? Well, notice that 1, 1 is indeed an identity because 1, 1 times anything is what I started with. So we would have a commutative ring with unity. However, we wouldn't have an integral domain here because we do actually have zero divisors. Namely, 1, 0 times 0, 1 is 0, 0 in either direction. And so we had two non-zero elements which multiplied together to get out 0. So we would have a commutative ring with unity which is not an integral domain and therefore not a field. In the same way we would talk about a subgroup of a group. So a subgroup of a group is a subset, which is also a group. So if we're going to find a subring of a ring R, we're going to say that that's true if S is a subset of R and S itself is a ring. Note that we've already shown that Z and Q are rings, but if we also note that Z is a subset of Q, that is, every integer is indeed a rational number, what we get is Z is a subset of Q, Z is a ring, Q is a ring, therefore Z is a subring of Q. The other thing we use with groups is we used homomorphisms. So much the same way we defined a homomorphism from groups was one that respects the operation. Well, if we define a homomorphism between rings, it's going to be a mapping which respects both of the operations. So that is, if I take alpha of A plus B, then that's going to be alpha of A plus alpha of B. And if I take alpha of A times B, that's going to be alpha of A times alpha of B. And so that's what's going to be a ring homomorphism. So if we want to find an example of a ring homomorphism, note that we can map the set of integers to the set of integers mod n, given by I'm going to map x to x mod n. So if I want to show this as a homomorphism, I really just need to denote that, hey, this is well defined. If I start with x, I get one solution when I find x mod n, therefore I have a well-defined mapping. If I then move on and say, well, does this respect the addition? Well, we've proven in the past that mod n does indeed respect the addition. That is, if we take A is congruent to B mod n and C is congruent to D mod n, then A plus C is congruent to B plus D mod n. It also respects the multiplication. So A times B would be congruent to C times D mod n. So this indeed would be a ring homomorphism. Something new for rings that we didn't really talk about with groups is we can talk about taking a ring and adjoining an element A. So we would say R adjoin A is going to be the ring which is constructed by transitively closing the ring under addition and multiplication once we have added A into the set. So the idea is we take the ring, we just throw a new element in there, and then we transitively close it under multiplication and addition. So if A is in there, then A times A is in there, and A plus A is in there, and A times A times A is in there. But also, if I take anything in R times A is in there, and so on and so forth, until we have a new closed set. So for an example of that, let's look at the integers adjoin the square root of 2. So we're going to have the integers, we're going to throw the square root of 2 in, and we're going to want to close this set transitively under addition and multiplication. What we claim is that that's going to look like A plus B times the square root of 2 such that A and B is in Z. So we'll actually go ahead and show that. Alright, so to look at what the integers adjoin the square root of 2 would look like is I'm going to take this one step at a time and just think, well, what do these things look like? Well, I know the square root of 2 is in there. So I also have to have the square root of 2 plus the square root of 2. So that would be 2 square roots of 2. I could also add again, and I get 3 square roots of 2, 4 square roots of 2, 5 square roots of 2. And so in general, I know that I can get things that look like b times the square root of 2, where b is an integer. I also have to get, well, that was adding, so I can multiply. The square root of 2 times the square root of 2, though, is just 2, so that's an integer. If I multiply by the square root of 2 again, I get 2 square roots of 2. And then I get 4, and then 4 square roots of 2. But notice I already have things of the form any integer times the square root of 2 under addition. So when I multiply, I'm just getting more things of this form. So if I'm trying to find just what do all the elements look like, well, I have that. This takes care of addition and multiplication, just starting with the square root of 2. Now, if I add in other integers, what I would say is, well, if I have b times the square root of 2, and I want to close this under multiplication by some other integer c, so let's let c, b, and z. If I multiply by c, b, square root of 2, what I end up with is c times b times the square root of 2. So notice that cb is an integer, so we just end up back in this case, so we're closed under multiplication. If I think about addition, what I end up with is c plus b times the square root of 2. So now I do end up with something new, and so now I'm going to end up with, okay, well, I have all the things of the form c plus b times the square root of 2. Well, instead of c, let's call it a then, such that a and b are integers. So inside of the integers adjoin the square root of 2, I can get anything that looks like a plus b square roots of 2. So I've tried to close it under multiplication and addition, and then I added in integers and closed it under multiplication and addition. And I just want to go back and check now. Well, if I multiply this by the square root of 2, I get a square roots of 2 plus b times 2, well, that's still something of this form. If I add a square root of 2, well, I can pull that back into this term. If I add another integer, I can pull that back into this term. If I multiply by an integer, well, an integer times an integer is an integer. And so I do indeed get that. If I take the integers and adjoin the square root of 2, I'm going to get all of the elements of the form a plus b times the square root of 2, where a and b are in Z. And this is the set I get after closing transitively under addition and multiplication. Now, if we start off with a commutative ring and we joined an indeterminate or a variable, say x, so something that doesn't have a relationship to the pre-existing numbers, then what we end up with is r adjoint x, and this is going to be called the polynomial ring over R. So that is, we're just going to throw in an x, and so we're going to get things like x, x squared, x cubed, but also add those together and multiply by anything in the original ring, and that's what we're calling a polynomial ring. With that in mind, let's actually go through and figure out what the polynomial ring over the set of integers would look like. So what types of elements would we get out? Alright, so if I work with an indeterminate x now instead of the last case we had the square root of 2, we're going to do the same process. It's just the big difference is that we don't get something like the square root of 2 times the square root of 2 is 2 to get things to simplify. So in particular, if I start with x, I have to close this under addition, so I should get x plus x. So 2x should be in my set, plus x, so 3x should be in my set. And so I should get anything of the form, let's say, a sub 1 times x, such that a sub 1 is an integer. So to close it under addition, I just get all the things of the form of an integer times addition. Also, if I move on and say multiplication, well, I'm closing under multiplication, so I get x times x is x squared, times x is x cubed, times x is x to the fourth, and so really I get anything of the form x to the n, but also I get anything of the form x to the n for any n, so n a natural number, and then I can multiply by any integer, so I get all the things of the form, well, say a sub n times x to the n, such that this is an integer, because I know that, well, if I have x to the n, I can add, and I can also subtract because we're closed under additive inverses. So I get, well, a to the n times x to the n is going to be in there for every integer a n and every natural number n. But if I can put in that together, I get a sub n x to the n plus a sub n x to the n minus 1 plus dot 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 plus a sub 1 x plus a sub 0, because I'm taking all the things of the form a sub n x to the n. So a0, we're going to consider x to the 0 to be 1, a1 x to the 1, a2 x squared, a n minus 1 x to the n minus 1, a n x to the n. And so I'm adding these things all together and I'm getting that. Now notice that I do have to stop somewhere. So I have to have a highest power, which would be the degree of my polynomial here, because if I can't add infinitely many times. So I don't have an infinite addition, so I do have to stop at some point in order to have a polynomial here, so I would end up with things like this. Now I know that I'm going to get things like this. Now I could say, well, can I multiply x by this thing as well? And notice that then I should get something like a to the n, x to the n in there. But what we're going to say is because we're defining this over a commutative ring, the multiplication with x will also be commutative. So this becomes a to the n, x to the n minus 1. So again, we'll get something that looks like this, which we can then add together. So multiplying by x's is going to be in here. If I multiply two things of this form, I can use the distributive property for my ring to get out, well, it's going to look like another polynomial. If I add two polynomials, well, if I get 5x squared plus 6x squared, that's going to be 11x squared. So yes, that's still going to be in there. So if I add x to the m plus x to the m times some other thing, I'm going to end up back in here. If I multiply by an integer, well, an integer times an integer is still an integer, so I end up back in here. If I add an integer, well, that's just adding an integer to here, so that's still an integer. And so if I look at this and I say, okay, well, I started off with x. I said I can add as many as I want, I can multiply as many as I want, and then I can add those things together and add in and multiply by integers. What I get is that the polynomials over the set of integers is just going to be of the things of the form p of x is equal to a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus a sub 1 x plus a sub 0. So for a sub I an integer and n a natural number. All right, or 0. So union 0. Because if I say x to the 0, that's 1, and I could just get a constant. A to the 0, or a sub 0 would also be in the polynomial ring. And so again, just closing this off, that's what we end up with. And so that's what we're going to call a polynomial over the set of integers. We could also work with another set instead of the integers, like the rational numbers. Then these terms just become, well, they can be rationals instead of just integers. Or if I work over reals, these can be reals instead of just integers. Thank you for joining me today. I appreciate that you stuck around to learn about rings. Hopefully you enjoyed it and learned something. I know that was a really quick overview of rings, but I wanted to introduce you to some important things about them and make some connections back to groups and explain the types of things that we'd be looking at if we had a different type of algebra other than just groups.